Galactic antinuclei travelers could help illuminate dark matter. The antimatter counterparts of light atomic nuclei can travel vast distances through the Milky Way before being absorbed, new findings have revealed. As these particles travel, they potentially act as messengers for dark matter. So the revelation could help astronomers in the hunt for dark matter, the mysterious substance that accounts for around 85% of the universe's total mass, but remains invisible because it doesn't interact with light. Welcome back to the Space Gaze. Before we proceed, kindly subscribe to our channel and hit the bell icon to stay updated when we release new videos. Without further delay, let's dive in. Scientists at the ALICE collaboration arrived at the finding using antihelium nuclei, the antimatter equivalent of helium nuclei, created by collisions of heavy atomic nuclei at the Large Hadron Collider. Our results show, for the first time on the basis of a direct absorption measurement, that antihelium-3 nuclei coming from as far as the center of our galaxy can reach near-Earth locations. ALICE physics coordinator Andrea Dainese said in a statement. Although this form of antimatter can be created in particle accelerators like the LHC, there are no natural sources of antimatter nuclei or antinuclei on Earth. However, these antiparticles are produced naturally elsewhere in the Milky Way, with scientists favoring two possible origins. The first suggested source for antinuclei is the interaction between high-energy cosmic radiation, which originates from outside the solar system, with atoms in the so-called interstellar medium that fills space between stars. The other suggested source of antinuclei is the annihilation of dark matter particles that are spread throughout the galaxy. While scientists know little about dark matter, they are certain that it is not comprised of particles like protons and neutrons that make up the everyday matter that forms stars, planets, and us. Scientists believe dark matter, in contrast, is comprised of a wide range of particles with colorful names like WIMPs, weakly interacting massive particles, and MACHOs, massive compact halo objects. One scenario suggests that when dark matter particles collide, they annihilate into particles that then decay into light matter and antimatter particles, like electrons and their antimatter counterpart, positrons. If dark matter annihilation is indeed a source of antimatter in the universe, antimatter could point the way to dark matter, scientists hope. Calculating the flux. The quest to learn more about dark matter has prompted the development of space-based missions, such as the Alpha Magnetic Spectrometer aboard the International Space Station. AMOS was designed at CERN, the home of the LHC, to search the cosmos for light antimatter nuclei that could indicate the presence of the mysterious dark matter. But in order to determine whether dark matter is the source of antinucleons, scientists operating AMOS and similar experiments first need to know how much light antimatter can pass through the Milky Way to reach their near-Earth locations, also known as the antiparticles flux. This flux is dependent on several factors, including the antimatter source, the rate at which it produces antinuclei, and the rate at which the antinuclei disappear as they journey from the center of our galaxy to Earth. This disappearance occurs when antimatter particles meet particles of traditional matter. Either both are annihilated or the antimatter is absorbed by the matter. The ALICE collaboration investigated the disappearance of antimatter by using the LHC to collide lead atoms that have been ionized or stripped of electrons. The physicists then measured how antihelium-3 nuclei created by these collisions interact with normal matter in the form of the ALICE detector. The experiment revealed for the first time the rate at which antihelium-3 nuclei disappear as they encounter ordinary matter. The results also predict the characteristics that antiprotons and antineutrons are likely to exhibit if they come from interactions between high-energy cosmic radiation or dark matter. They are likely to lay the foundation for future studies of dark matter. According to observations of the gravitational effects in the Milky Way, estimates suggest approximately 85% of the galaxy is made up of a substance which is not visible in light or radio wave detectors, hence dark matter. Scientists have so far found it impossible to directly prove the existence of the material, something of a stumbling block in the quest to achieve a complete explanation of the cosmos. Using data from a Large Hadron Collider experiment, a project at the LHC, the researchers were able to uncover key features of the behavior of antinuclei, which could help understand when they have resulted from interaction with dark matter. Antihelium-3 nuclei were produced in particle collisions, then interacted with matter in the ALICE detector, causing them to disappear. The resulting data was entered into a publicly available computer program called GALDROP, which simulates the propagation of cosmic particles, including antinuclei, in the galaxy. The researchers looked at two models of the flux of antihelium-3 nuclei expected near the Earth after the nuclei's journey from sources in the Milky Way. One model assumes that the sources are cosmic ray collisions with the interstellar medium, and another describes them as hypothetical dark matter particles called weakly interacting massive particles, WIMPs. The model offers an analysis of the transparency of the galaxy to antimatter, how much of the material is likely to pass through space. The ALICE researchers showed about 50% transparency for interactions with dark matter and about 25% to 90% for cosmic rays, depending on the energy of the antinucleus. This is an excellent example of an interdisciplinary analysis that illustrates how measurements at particle accelerators can be directly linked with the study of cosmic rays in space, said Fabietti in a statement. The results, published in Nature Physics Today, are of great importance for the search for antimatter in space with the AMS-02 module, Alpha Magnetic Spectrometer, on the International Space Station. Using a computer program, the researchers then simulated the propagation of antiparticles through the galaxy and introduced to this model the disappearance rate measured at ALICE. This model allowed the researchers to extrapolate their results to the galaxy as a whole and to look at the two suggested mechanisms of antinuclei production. One model assumed the antimatter came from cosmic ray collisions with the interstellar medium, and the other model attributed antimatter to a hypothetical form of dark matter called weakly interacting massive particles. For each of these mechanisms, the ALICE team estimated the transparency of the Milky Way to antihelium-3 nuclei. In other words, the distance antihelium-3 nuclei are free to travel before being destroyed or absorbed. The models reveal the transparency of around 50% in the dark matter model and a transparency ranging from 25% to 90% in the cosmic ray collision model, depending on the energy of the antinuclei created. The results could be important in future experiments that count how many antinuclei arrive around Earth, and with what energies, in hopes of determining whether the origin of these antiparticles is cosmic ray collisions or dark matter annihilation. Our findings demonstrate that searches for light antimatter nuclei from outer space remain a powerful way to hunt for dark matter. ALICE spokesperson Luciano Musa said in the same statement. Antimatter from far away should be tricky to find. It annihilates when it meets regular matter, and the more space it crosses, the more chances there are for these particles to meet their end. But an experiment at a particle collider suggests that some antimatter particles can travel across our galaxy without getting destroyed. In space, the antimatter version of helium atoms nuclei, the antihelium nuclei, are thought to form when cosmic rays collide with free-floating atoms. Theories suggest they also arise when particles of dark matter, a mysterious substance that fills most of the universe, annihilate with each other. If antinuclei made in such annihilations were detected, they could reveal new properties of dark matter. That's all I have for you guys for today. If you liked watching this video, please make sure to click the like button, subscribe to our channel, and click the bell icon so that you may be notified when we upload a new video. Thanks for watching.